Recording's rolling. It is Thursday, April 17th. All right, so one thing is, admin was talking to the physics teachers and saying they're some classes short of getting enough physics classes together. There's some issues with that. And also, we're trying to promote the AP program in general. Now, of course, you guys are in AP1. Okay, and I know a few weeks ago you guys signed for schedules for what you wanted for next semester. Right, but I'm going to ask my classes again if you thought about this more, if they'd be interested in taking AP. Right, and so I'm going to put some lists together and then send that to admin. So since you guys are in AP1, this one says interested in taking either AP2 Physics 2, which is algebra based, or AP Physics C, electromagnetism, right, which includes calculus. It's supposed to be calculus based. Right, so if you already signed up to take this, then that's already in the books and probably ready to go, right? Guys, if you had not signed up for AP Physics 2 or the calculus version of it, these are pretty similar classes, just one's algebra based, one's calculus based, right? And you're thinking, that would be a good opportunity. Then here, I'm going to pass this page around class and this opportunity to sign us, and I can give that to admin and they work from there. So I'll just send that around. If you're interested and you hadn't signed up before, signed up. If you're not interested or you already signed up, then go ahead and just pass that around and there you go. It's another opportunity. All right, what's what we got here? Oh, what I didn't write here is we got 29 days until the exam. Of course, you guys have lots of study materials you guys have to do. Right, but you know what else is exam schedules? So the exam schedules have been released. I did post these to Google Classroom. Now, the regular exam schedule for most students is going to be May 22nd through 28th. Looks like this. Seniors always take their exams a little bit early. So it's going to be the 12th through the 16th because, of course, graduation and then everyone else is still going to class. Right? Now, you guys for this particular class do not have a final exam because you guys have the AP exam instead. So everybody who's showing up to class during these weeks will just do other types of activities. I mean, it'll definitely make it worth your time to show up to class. But
Can we still have like an activity or something just for the
credit? I don't know what, I don't have anything specific planned right now, but yeah, it'll be some kind of activity. I've got some ideas, right? If nothing else, I'll at least have like books and board games for you guys or let you guys study. But at least you guys can talk with your friends or something, right? But all right, so those schedules are posted and more relevant to your other classes. You guys remember yesterday we started talking about electricity and circuits. I know I gave you a bunch of information, all I could in 45 minutes and whatnot. And I gave you guys this page. So there's some circuits on one side. There's some Kirchhoff cables on the other side. We'll be getting to those shortly. You guys have on your desk, do you guys have some 9-volt batteries? Oh, they're brand new. They should be still plastic wrapped. You guys go ahead and open those, your 9-volt batteries. You guys should have some paper clips, which might be helpful to extend the leads of your batteries. Right, maybe not. I don't know. I'm trying something a little bit different. I'll show you guys how I normally do this lab, and this is going to be a new tech lab. But you could, if you want to, take the paper clips and extend the leads of these batteries. Now, careful though. Make sure that guys, do you want to make the metal touch so that the leads there's a direct contact between leads? The answer to that is no. It'll get really hot really fast. Might catch the paper on fire. And it would drain the battery really fast, and all those would be fruitless. Because that. Also got you guys got some Christmas lights, which are resistors. We're going to string up some of these circuits. You guys remember at the end of class yesterday? I think it was about the last 5 minutes of class. You guys remember Paul Hewitt had that car battery that was 12 volts, and he was stringing together different types of circuits. Right, so you guys can do that here. All right, and then we'll get to that circuits and Kirchhoff page too. Right. So again, if we were doing this properly, I'd probably take at least a couple of weeks to do this with you guys, but I'm trying to condense this into a few days. So getting back to the review. Right. But I don't know. In case just if you're interested in context, or if you're teaching physics yourself one day and want some options, how I normally to do this lab is. Do you guys see a cell phone charger right here? This is going to be 5 volts DC. It says on here. I don't know if you guys can read it. It's kind of fuzzy, but it says 5 volts direct current. Guys, what's the other kind of current that's not direct current? It's called alternating current. And that's what's right here in this outlet. Hey guys, do I want to go shove anything in this outlet that's not supposed to go in there? No, because big old fireballs can come out of here, and then you got a field trip to the hospital and not good time. Guys, did I tell you guys, or do you know how many volts this is? 120. It's 120 volts alternating current. But if I plug this in, that takes 120 volts alternating current down to 5 volts DC, which is these two leads right here. Guys, is it safe to touch these two leads? Yeah, 5 volts DC. In fact, I could. Let's see, wire this up. Oh, look, it lights up the bulb. Look, there you go. Okay. Now, I do have a set of these cell phone chargers, but again, trying something a little different. So instead, we're going to move over to the battery. So you guys got 9 volts. Ooh, that's almost twice as much. That's a bit brighter, isn't it? Ooh. Okay, so we'll try that instead. Play around with that. Okay. Yeah, let's go ahead and wire some of these up, and I'll draw some schematic diagrams as we're going along so you can see what pairs to what. Oh, multimeter. You guys have multimeters. That's what else. Okay. So again, if this was a full proper lab, I would. Okay, we're gonna do a short version of this. Make do what we can here. Right. So guys, this multimeter. Now, multi means multiple, right? So there's multiple things you can measure. You can measure both current and voltage with this, but in different ways. Let's see if I got some. I know I have a poster for this too.
No.
Hang on. There. Okay, here it is. Here it is. Okay. So here, you guys see this poster? You guys see this poster? So depending on what you're measuring with the multimeter, you actually have to wire up your circuit differently. Okay. So you guys see right over here is a battery. You guys see this battery? Right. That's what this is. The voltage source, the battery, right? Right. You guys have 9 volts. Right. Guys, what is this jaggedy symbol right here? A resistor, exactly, which you guys have a Christmas light to represent a resistor, right? So do you guys see that to measure the voltage, which is really a potential difference? It's really a change in voltage. You want to connect it in what's called parallel. So you're saying, what's the difference in the voltage between this location and this location? Okay, that's different than measuring current. So when we get down to current, you have to make some changes in the multimeter. Here you get the ammeter aspect. Do you guys see for current, actually, you actually break open the circuit and you force the current to flow through the multimeter, through the ammeter? You guys see it's a different setup, right? That's called in series, right? Right, so just be aware of that as we're going on to measure these things. And so we'll get to this. Actually, let's try one right now. So you guys have 2 leads, but you guys have 3 places to plug things in. Also, guys, there's different versions of these multimeters. I try to get you guys the best ones. If you have an orange one, it's probably really good. Those tables over there, if you have the yellow ones, those might work. If not, I left the bucket over there for you guys. You guys see a big old bucket of multimeters? If it's not working very well, then try a different one or team up with a different table. All right. So I tried to get everyone a good one if I could, but the orange ones work the best. So you have to switch tables and whatnot. That's okay. Okay. So guys, take the black lead and plug it in where it says COM, C-O-M. It's probably in there already. Okay. Now take the red lead. Is the red lead plugged in the one that says not amps or 10 amps or anything with an A, but one says like volts and ohms and something. Okay. So if you guys have COM and volts, again, there's a little bit different models, so yours may or may not look exactly like mine. Okay. You guys got those? Now let's toggle switch. I see a bunch of toggle options. We're going to switch over. Most of these I think are in the top left. You guys see V for voltage. And there's a flat line across it as opposed to a wavy line. The wavy lines are alternating current. We're not working with that. So we're working with batteries. That's the flat line. Do you guys see that? Now, if you switch the toggle switch, it just moves the decimal around. So different levels of precision. Maybe I'll leave it right there. See what happens. So let's try the battery. Should this be 9 volts? Do you guys think 9 volts? Let's try it. Let's go lead to lead. You should get. Oh, look at that. 8.7. Whoops. Get it out of the glare. Well, mine says 8.7 volts. 8.7 volts. That's about 9 volts. You know, a little plus or minus background. That's okay. Now remember, this Amazon battery yesterday was not making the bulbs as bright. So let's see what is this. 7 volt. Actually, if I switch the leads, I'll get the positive value. There you go. About 7 volts. Okay, yeah. So it's missing a little bit. That's all right. Okay. 7 volts, 9 volts, something like that. All right. Let's make a connection here. I know every one of you has a battery, right? Everybody individually has a battery. You guys have to share the multimeters if you want to use that. And so, guys, go ahead and throw a Christmas light across the lead. Can you guys light that up? No. All right. So what you just created is this right here. Right, get just created that right there. Now let's try this. What if you put 2 bulbs in a row or 3 bulbs in a row? I'll just cut straight to 3. Saves a little time. Okay. Do you guys see these 3? This is called in series. 3 in series. Okay. So I could take 3 like this. Right. Guys, it's okay to twist tie the Christmas lights together. This will probably last a few years. Now I'll just buy some more. Right. You guys see I have the ends twist tied together? But guys, go ahead and take 3 bulbs, one after another, and twist them like that. You guys see that? Right. And put that across the leads of your battery. Ooh, it lights up, but it's they're definitely dimmer than before. You guys see it? Definitely dimmer. Right. Now, how bright they are is related to power in watts. So when we get to the Kirchhoff tables and those circuits, we'll see those numbers more. Okay. Right, something like that. How about this? Since you guys got the multimeters, you always have to share these around or work with each other. Let's see how much current is actually flowing through 1 Christmas light compared to through 3 Christmas lights. So, actually, let me try voltage. Since we got voltage fired up, let's try voltage. So I got these hooked right here. Okay. I wonder what the voltage drop is across 1, 2, or 3 bulbs. And the voltage should drop a little bit. So guys, the voltage should add up to what? 9 volts, or pretty close to 9, maybe it's like 7 or 8, 9, something. All right, so let's see. I'm gonna switch this back to volts, DC volts. Okay. Connect. Now you guys see 2 terminals, one small and one's large. The small one's the positive, which is the red lead, and the large one is the negative, which is the black lead. Okay. So here I'm gonna have these wired up so they're already lit. I'm gonna connect the red to the small one, and if I connect the black to the big one, look, I'm getting I should be getting 9 volts. It's showing most of it. It's showing like 7 point something. Okay, so most of it's there. Is that okay? 7 volts. It's almost 9. That's all right. Okay. All right. Now, what if I go across 1? I want you guys to predict if I connect just across this one. Do you guys think it'd be about a third of that? Maybe about 2 or 3 volts. Do you guys think about 2 or 3 volts? Let's see. Yeah, it is. It is about 2 or 3 volts. Look at that. Hovering around a little bit. It's about 2 volts. So, right. Guys, what if I connect it right here to go across these 2 resistors? What do you think it's going to be about? About 6 volts? Yeah. Okay, 5 point something. That's pretty close, right? 5 point something volts. All right. You guys getting success too? Still working out? Right. Let me see. So that should work. If it doesn't, then go ahead and jump in and has more work. All right, you guys all right? We being all right? All right, let's try a current test. Now, guys, there's only one. Well, here, I'll do it for just 1 volt first. Now, for current, you guys remember I have to break open the circuit and force current to flow through. Also have to make some changes on the multimeter. All right, you guys ready to measure current in amps? You guys ready for this? Current in amps? All right, so I'm going to make a change. I'll leave the black lead in the COM, the black stays in the COM. I'm going to take the red lead. I'm going to pull it out. Guys, I just pulled the red out. I'm going to switch the red over to the side that says something to do with A, which is amps. You see that? Right? You see that? Now, again, there's different versions of these multimeters, so yours may be a little bit different version. But if you have this version, I'm going to switch this toggle to there's a particular one that says it says 200 milliamps, and it's direct current because it has the flat line over it. Right? So that works for this one. If you have a different one, then just make do see if you guys can figure it out. Right? And right now the circuit is open. See, I have 1 lead connected, so the bulb is definitely not lit up because it's an open circuit. So it's switched off. Right. Then I'm gonna connect the red to the bulb. Right. You guys see I got the red connected to the bulb. Now it's still not on because it's still an open circuit. But guys, watch. If I take the black lead of the multimeter and connect it to the negative terminal battery, is the bulb gonna turn on? Oh, it should have. Why didn't that turn on? That should have turned on. Wow, really? That's not gonna do it. Oh, there it is. Okay, bulb turns on. And I'm getting 2.7 amps. Do you guys see 2.7 amps right there? 2.7 amps? All right, 2.7 amps. So this one's 2.7 amps. In fact, while you guys are trying that, I'm gonna Follow Ohm's law for this. You guys remember Ohm's law from yesterday? Says, yeah, current is voltage over resistance, right? So this is current. Here's your voltage, also called potential difference. Sometimes you see a delta V right here. Okay. And this would be resistance. Okay. So I just measured current to be 2.7 amps. That goes in for that I, right? Okay. And the battery voltage, what was it again? Like well, I'll call it 9 volts. So depending on how I measured it, 7, 8, 9 volts, somewhere in there. Okay. Ooh, guys, could I calculate what is the resistance of this light bulb right here? Can I calculate that? Okay, so little algebra switch, little shuffle right here. So it would be 9 over 2.7. Okay. So I'm getting a resistance of 3.3 ohms. Okay, that's what I got. Now, having done this lab so many years, that's kind of on the high end. I normally see anywhere between 1 ohm and 2.2 ohms, somewhere there. Okay, so you should get somewhere in there. Because for the resistance of your own bulb, if you do the same thing, measure voltage, measure current, apply Ohm's law, you should get somewhere between 1 and 3 ohms. Are you guys trying that out too? Somewhere between 1 and 3 ohms? Right. Okay. Go ahead, work at your own pace. Just for the video, you can always go back and watch this video later. Trying to keep a little bit on the fast side here. I'm gonna go ahead and try out this 3 resistors in series and see if I'm still getting similar results. So let me try my voltage here for 3 and well, actually I know it's 9 volts. I'll just skip that. Let's cut straight to current because I got the slide queued up for current anyway. Okay. So let's see what current am I gonna get. All right, so switch this over to current milliamps. Connect here, get both side up. All right, is this gonna do something for me? Okay, it says 1.6 amps. Right. Ooh, guys, that's less current than before. Remember before I was getting like 2.7 amps? Now I'm getting 1.6 amps. 1.6 amps. That's across all 3. You know, it's kind of hard to see. My hands are in the way. But I broke open the circuit and I put the leads of the multimeter to force the current to flow through the multimeter. I got 1.6 amps. So let me try that. Let me try Ohm's law. I equals V over R. Okay. Now this time I was getting 1.6 amps. I'll just call it 9 volts. Okay. But guys, 3 resistors in series. I think we talked about this very briefly close to the end of class yesterday. Is the total resistance, you just add them up, and and if they're all the same, could you sort of call this 3 times the resistance of an individual one?
Yeah. So
in place of this generic R, I'm going to put 3 times the resistance of a single bulb. Is that okay? Is that okay? Where this R represents the resistance of a single bulb. Okay, and I'm interested to see how close does this match this. So 3R equals 9 volts over 1.6 amps. Little switch right there. Divide this by 3. What is 9 over 1.6? And then divide that by 3. Right. Okay. So this time it worked out a little different. That's okay. I'm getting resistance of 1.88 ohms. Right. Kind of like I was saying before, I was thinking this was kind of on the high side compared to what I'm used to seeing from this lab. Right. So a little bit different way of setting up and measuring it. Ideally, it'd be the same, but not far off. About 2 ohms. Okay. You guys get about 2 ohms somewhere in there? Right. All right, let's try a different setup. Here, I'll just do 2 in parallel. Can you guys take 2, tie the leads together? Guys, go ahead and tie 2 leads together. So leads there. Right. And I'll draw a schematic diagram of. Oh, yeah, thank you. Right. So here I got this AP list. Guys, who else wants this AP list? Doesn't have this AP list yet. Anybody else want this AP list? Right. So I got this AP list right here. If you still want to sign the AP list, yeah. Glad to see some of you guys are signed up there. That's awesome. Right. So if I connected 2 bulbs in parallel. Now we're back to really, really bright, kind of like originally. Each bulb is as bright as the individual one was individually. Right. So what does that schematic diagram look like? So this is in parallel. 2 bulbs in parallel. 2 bulbs in parallel. Okay. So the schematic diagram I would represent like this. Okay. You guys see how that's different from in series? Here, if you look at the series setup, you guys see there's only one track for all the current to go through. It has to go through all 3, right? Sequentially, one after another. Right? But with the parallel setup, you guys see the current's going to split, and maybe half the current goes one way and half the current goes the other way. You guys see that too? Right? And then it goes back together and creates circuit, right? And so, let's check this out. What do I want to measure here? Oh yeah. How long would it take the battery to drain? Well, somewhere around here it says how much energy is in it. It would be a simple calculation. It's like distance equals speed times time. It's really that. It's like how much energy. It's guys, it's energy equals power times time. Right? Energy is power times time. Right? Or wait, is there another way to say this? Here's another way too. Right. Yeah, energy, work, both in joules. I don't think it says in joules. Does it say? I forget. I'm not seeing it. Sometimes there's another unit. I want to say it's like amp hours or something weird. I don't know. So yeah, part of that way. Hey, but I can hear though. Right now, guys, if this is a 9-volt battery, is there 9 volts going across this one and also 9 volts going across this one? Yeah. Now that wasn't true for series. For series, it'd be like drop 3 volts, 3 volts, 3 volts, drop 3 volts at a time. But for parallel, there's 9 volts going across each of them. Okay? So what I'm going to do is break open the circuit. Guys, if I break open the circuit here and measure the current, versus if I break open the circuit here and measure the current, I should get 2 different currents. Like here I should get the 100% of the current. But since it splits half and half, for this one, I think I should get just half the current. Right, let's see if I can do that. So, got my battery, got this set up to measure current in amps. Got my, okay, this is right here. Okay. So first I want to get the total current. And the current here should be half, but let's see if that's true. Switches the current. Okay. So connect this, connect that there and here to get the positive value. Okay. Get this out of the glare. There we go. Okay. Sorry, that goes there, here. Okay, bulbs are lit up. I'm getting 5.1 amps. Well, 5 amps. You see 5 amps right there? It's fluctuating a little bit, but 4.9, 5.1. We'll call it 5 amps. So down this track, I'm getting current is equal to 5 amps. Okay? I broke open the circuit. I forced the current to flow through the multimeter. Okay. Now let me try. What if I break it open here? Okay. Do you guys think maybe I'll get closer to 2.5 amps? I should 2.5 because 2.5 amps down this track, 2.5 amps down this track, add up to 5. Okay. See what I can do here. So I need to break this open right here. Okay. Oh look, now I got this going on. Okay. So connect this lead here. It's off. This lead here. Okay, so now I got 1 bulb on, 1 bulb off. Okay. That's okay. They were both about to turn on as soon as I connect the multimeter here. Okay, so connect this here. Is this out of the? Okay, it's out of the glare. Good. Connect that right there. Okay, now they're both on, and I'm getting. Oh, it is. Look at that. You guys see 2.4 amps? 2.4 amps. You see that? You see that? Right. There, I'm gonna round it a little bit just for the math. But that's all right. I'll call it 2.4 amps. That's exactly what I was reading. So the current here is 2.4 amps. You guys see it definitely split about half and half, didn't it? You see that too? Okay, here we go. Okay. All right. I want to build one more circuit with you guys, and then we'll go over to that page. Okay. Okay. All right. Ready for one more circuit? Let's do a hybrid circuit. Here, I'll draw the schematic first for this one. Let's do. I want to do this. Here, I'm gonna steal an idea off this page. Okay. How about this one right here? You guys see number 6 on your page? Number 6. Let's try that one. So I'll have some voltage source. I'll have one resistor connected directly to one lead. and then the other lead of that resistor is connected to a couple of bulbs in parallel, and those are both connected to the other lead of the battery. Right? So do you guys see that these two would be in parallel with each other, and they connected in series with this one? You guys see that? So now we have like a hybrid setup. This is neither pure parallel nor pure series. It's a little bit of both. Right? Do you guys think these bulbs are going to be different brightnesses? You know what? Actually, after this one, I'm going to try a little bit different hybrid setup. I'm going to try number 7. I'll draw number 7 on here too. Let's try number 6, followed by number 7. Yeah, okay, that's different. Okay. Yeah. So I need 3 bulbs. Let's see, how can I do this? So this bulb can be connected directly to the lead of the battery. These two I have to tie together. Okay. Right, so I'm ignoring this one for now. I'm just going to create this one right here. It's right here. Okay. So guys take 3 bulbs. Whoops. Okay. Try that again. Whoops. Okay. Guys, take 3 bulbs. Can you guys put 3 bulbs? Just start them in series, 3 in series. Can you guys start that? Right. And then take these leads right here and tie them together. We're just going to put these 2 in parallel. So it should look like that. You guys see in my right hand, I have 2 in parallel, and then my left hand is connected in series. You guys see that? Right. Go ahead and make that. Did you guys all tie that together right there? That's all right about that? Right. Now that, you got to connect straight to the lead in the battery, and this is exactly what this schematic diagram is showing. You see that? Okay. Here, I'll pick the positive over here just to make it exactly match the picture. And oh, look at that. Or maybe I should have you guys predict which is going to be bright, which is going to be dim. Right. But do you guys see that? Does it make sense that this one would have to be the bright one? Because all the current is forced to go through this. Right? Versus by the time you get to these 2 bulbs, doesn't the current split half and half? So they're relatively dimmer, aren't they? In fact, they look a lot dimmer. Ooh, look at that. You see that too? Everybody right? Okay. Okay. All right. And then, well, you could of course use the multimeter to measure voltages and currents at different locations. Okay. All right, let's do this one over here. So I'll cover this one up. Okay. So this one, that's a different setup. How can I make this one? Oh, I know how. Let's start with a triangle. So I'm gonna pull this thing apart. Okay. So you guys start by making a triangle out of your resistors. This is different. We haven't done this one yet. Okay. You guys have a little triangle loop? Okay, go ahead and tie that together. Go ahead and tie together a triangle loop. All right, everybody's got a triangle loop all tied together? Okay. Now, these bulbs I don't have to do anything else with. All I have to do is pick any 2 of these leads, like here and here, these wires. Then I come straight to the battery. Right? And that would create my circuit, which I'm right about to do. But right before I connect it, I just want to ask you guys, are all 3 of these going to be the same brightness if I connect them like this? You're right, they will not be. What do you think is bright? What do you think is dim? What about this one right here? Is this guy bright or dim compared to the other 2? Bright. Okay. And you guys can see why? Guys, if this is a 9-volt battery, how many volts does this one get across it? All 9 volts. All 9 volts. Actually, what I'm sort of revealing to you guys right now is called Kirchhoff's loop rule, which I didn't mention yesterday, but see if I can get to today possibly. Okay. Which is, if there's 9 volts here, all 9 volts drop across this. But down the other track, because the current's going to split, do you think maybe about 4.5 volts drop here and 4.5 volts drop here? And so these 2 should be dimmer? You guys see that? Right. So let's see if that's true. Right. So yeah, this guy should be bright and these 2 guys should be dim. Let's see if that's true. Yeah, that is exactly what happened. You see that? Right. Or if I just pick it up and rotate it 120 degrees, now I've changed position of bulbs. Now this guy should be bright and these 2 guys should be dim. Just to show you that it's not having to do with the bulbs themselves. It's just the geometry. Yeah. Or pick it up, rotate it 120 degrees. Now this guy should be bright and these 2 guys should be dim. Let's see. True. Oh yeah, physics for the win. Like I said, and those are all just this one right here.
No.
Right, yeah, nice. I see you guys making it. Yeah. All right, you guys doing all right? All right so far. They did good. Oh, yeah. Ooh, yeah, because you're putting 2 volts and two batteries in series. Yeah, that's what I didn't talk about. But yeah, if you're taking okay, yeah, if you combine batteries, you can put them in series. Guys, if you put 2 batteries in series like this, do you think this adds up 9 to 9 makes 18 volts like that? Yeah, so you could double the voltage. If you double the voltage, go back to Ohm's law. I equals V over R. If you double that voltage, are you doubling the overall current? And then I don't think we talked about Joule's law yet today, but power is current times voltage. You would also be doubling the power, wouldn't you? Yeah. Well, okay. Is there a limit to how bright the bulb can get? I mean, at some point, you're maybe run to a material limit, right? Like I've had some little tiny LEDs that I know if you put too many volts across them, you go, and they just die. So I guess you could like destroy the filament at some point. Yeah, that'll be a material question. Right? How's the filament made? Yeah. All right. How you guys doing? You guys doing all right?
Yeah.
All right. Okay. Okay. So, while I'm switching gears here, if you guys are still playing around a little bit, that's all right. I'm gonna do a quick review of what you guys saw yesterday, and then go into a little bit new material, and then try to work towards this page here, this circuits page. Okay, so from yesterday, you guys know there's charge is in coulombs. I think I charged up a balloon yesterday. Now, if you get that charge to flow, some number of coulombs per second flow rate, we'll call that current. Now, the variable is called I, and the unit is amperes. We'll put capital A for amps. Okay? Now, why would a current flow? Well, because there's some potential difference, like a voltage, like a battery voltage. So, got a AA battery here. Oh, I got this fun tool. Show you guys this works. All right, look, it's a good AA battery. Look at that. That little line which is the good mark. You guys see that little meter? This little meter says that the battery's good. It's also a 9-volt version of this. Let's see if yeah, positive there. Right. Yeah, see that needle just went to the green is good. But I remember the Amazon battery is like running out. Let's see what that one looks like. Ooh, it's in this yellow. Remember this one was showing like 7 volts. Yeah, so it's still working, but not as well as the fresh one. All right, so that's voltage. The battery provides a voltage. All these Christmas lights are resistors. The unit for that is in ohms. And you guys were getting probably about 2 or 3 ohms for one of these. You guys getting 2 or 3 ohms because you guys did a calculation from Ohm's law. Okay? Finally, powers and watts. Now, this you guys do know from last semester because that's joules per second. That's a rate of energy transfer. Okay? Okay. Which also tells you how fast is the battery being drained. Okay? Okay. And also it has to do with how bright is the bulb lighting up. It's all power in watts. Okay? Right. So we got electric field, look like this. That's where positive and negative or the field lines pull together. If you have what's the electrostatic force could look like that between 2 charges. Okay. Oh, here's a number of things you put on a circuit. Really, I just want to focus on these 2. So you got battery voltage and a resistor. Okay, that's mostly what we care about. Okay. Here's chemistry of a battery. Here's a flashlight schematic. Right. That's what you guys are creating little flashlights today, aren't you? Yeah, you guys got little flashlights on your desk. Ohm's law. So how much current flows is directly proportional to the voltage. So if you double the voltage, you double the current. Inversely proportional to the resistance. More resistance, the less the current. Ooh. Okay. Here's a water in a pipe analogy, which I remember all this electricity stuff clicked for me back in high school when I learned this analogy. Okay. Got that. Voltage is like pressure, current's like flow rate, and so on. Now, how much power flows? Here's 3 perspectives. You can go current times voltage. You also have current squared times resistance, or voltage squared divided by resistance. Okay, so they'll all tell you the same power in watts, right? You guys got that? Joule's law? Okay. Right. Joule's law analogy with the pipe, water pipe, which actually works in terms of the units, so it's fun too. Okay. Do you guys remember resistors in series? If you have one after another, they're all in the same street. You just very simply add the resistances together. You guys remember that?
Yeah, that works.
Okay. Now, you guys have also been wiring up some parallel today. Now, every time you wire another one parallel, from a macro point of view, from the point of view of this battery, what happens to the overall resistance? It gets what? More or less? Less and less and less. Less and less and less. You know what is the same math as this? Actually, guys, anything in parallel is this math. Yeah, I'm gonna well, let's go ahead and do this, guys. Let's go ahead and do this. Get ready for something fun because this will really click maybe when I show you guys the story. Okay, I usually ask the students a question like suppose there's a couple of guys who are painting a fence. Oh yeah, so some of you guys know this. Yeah. Right. So I'll draw a fence. Okay. And we'll call them Alan and Bob. It takes Alan
7 years.
let's call it 3 hours to paint the fence by himself. By himself. It would take him 3 hours to paint the fence. Now Bob, let's say it would take 4 hours to paint the fence. Okay. Now guys, if they make a two-man team, how much time would it take to paint the fence? Now, the fact that they're working together should it take them a lot more time or less time? A lot less time because they're helping out. We've got some teamwork going on. Okay. Does anybody know how to solve this? It is. It is. It's the same math as this right here. It is. Right. Now, before I check through this math, I want you guys to see that this would definitely be true. What if it was 2 Allens, like Alan and a clone of Alan? Guys, what if it was 3 hours and 3 hours? How long together? 1.5. I'm going to jot that down. 1.5 hours. Okay. What if it was 2 Bobs, 4 and 4 hours? How long would that take? 2 hours? Because half the time, right? Okay. So if we have 1 Alan and 1 Bob, should it be somewhere between 1.5 and 2? Right? Now, whether you do 1 over Alan plus 1 over Bob, and then take that reciprocal, which would be the answer? Or if you do product over sum, because there's only 2 of them. Again, this works for 2 people together. Okay. You should get the correct answer either way. Let me cut straight to the product over sum. So the time total to paint the fence. I'm going to do 3 hours times 4 hours over 3 hours plus 4 hours. This bit, I'll come out to some number of hours if you consolidate the units. So is that 12 over 7?
Oh no.
Okay, you guys, when I hit enter, I should get a number between what and what? 1.5 and 2. Let's see. 1.71. 1.71 hours. That's it. You guys see that? Okay. You guys think that could be useful later in life somehow, somewhere it's gonna show up in some situation in your life? Yeah, I don't know how. Right, there's like 20 of you guys in here, but if you're working in parallel, if you're working in teams, you're trying to figure out how long does it take to finish this project. Yeah, there you go. Okay. Same thing, resistors in parallel. Replace hours with ohms, and now you got resistors in parallel. Okay, you guys see that? Okay. All right. So I do have a bunch more posters. Let me hit some of those. Okay. So here I got a breadboard. If you're creating lots of circuits, you can do lots of fun things with breadboards. I've even seen people wire up components and create little robots to like drive around. But behind the breadboard, now there's a sticker here. If I pull it off, it'd be all sticky, but it would look like this. You got strips of metal. You have to know where the strips of metal go. So I can connect these resistors, right? And I got a couple of what are called rails or buses that go along the whole thing. So let me get that cell phone charger. Show you guys this does work. You guys remember this 5 volts right here? You guys remember 5 volts? Okay. So 5 volts. Now I do have a couple of LEDs here and a classic resistor. Now the LEDs, the electricity only goes one way. Oh, okay. Whoops. It was a coin flip. It actually was working. You guys see these LEDs lighting up? There's a red one and a green one. And so what's happening is this classic resistor is bridging the current across this gap right here. Right? This LED is bridging this gap right here, and this green LED is bridging this gap right here. But we have to bridge the LED, the gap, right? Because if I had a resistor, like guys, if I put, well, I have if I pull this out and I put this from here to here, if I go from the metal to the metal, is that ever going to light up? No, because the current, guys, what's the path of least resistance? Is it through the LEDs or through this metal strip? Yeah, through the metal strip. That would be the path of least resistance. So it shorts it out. So I have to bridge this gap right here and then make sure this turns back on. Yeah, right now we're back to turn it on. Okay. Right, so there you go. There's if you ever get deep into electronics, you're gonna be working with breadboards. There's your intro to breadboards. Ooh. All right, Kirchhoff's rules. Guys, everybody focus up here. There's a lot going on the slide. So there's really only two rules. There's what's called the loop rule and the junction rule, but all these other rules fall out of these. So I'll show you guys the full list. Now the loop rule says if you identify any loop within a circuit, the voltage has to sum to 0. Based on what you've been doing so far today, that should kind of make sense. If you're pumping up 9 volts, do you think 9 volts drop down in total? Now maybe it drops down 4.5 and 4.5. Maybe it drops down 3 and 6. It depends what these resistors are. But you'll have 9 up, 9 down, so that the sum of voltage in a loop is always 0. Hey, do you guys see a loop right here? Is this a loop? So if I have 9 volts right here, bam. Do all 9 volts drop across this one? And also 9 volts across this one? Yeah, because I have a full loop here. 9 volts up, 9 volts down. Or 9 volts up, 9 volts down. Yeah, that's all the loop rule. Okay. What else to say here? Well, I'm on voltage. Right. Right. I have a basic series setup and a basic parallel setup. Right. Oh, do you guys see? I mean, if you draw a logical conclusion, does the voltage drop always have to be the same across these two resistors? I mean, 9 volts up, 9 volts down, 9 volts up here, 9 volts down here. Wouldn't that have to be the case? Right. Now, what if these resistors are different? What if this is 1 ohm and this is like 10 ohms? Do they still have the same voltage drop? Yes, they do, because that satisfies the loop rule for a parallel. Okay. Right.
Oh, yeah.
So that's voltage. Right. Now the voltage drop in series is a little bit more complex. Do you guys see this proportion right here? So the voltage drop across resistor A is going to be very simply proportional to resistor A. So here's what I mean. Guys, suppose this is 1 ohm and this is 2 ohms. Are you guys give that 1 to 2 ratio, 1 ohm versus 2 ohms? Right? What this ratio says is that if you have a 9 volt battery, 9 volts, then a third of the total, because 1 over 1 plus 2 is not like a third of the total voltage drops across the 1 ohm resistor, and 2/3 of the voltage drops across the 2 ohm resistor. Is that okay? Okay. You guys, what is 1/3 of 9 volts? 3 volts. And what's 2/3 of 9 volts? 6 volts. So you're going to drop 3 volts followed by 6 volts for 1 ohm and 2 ohms. Is that okay? Okay. Right, that's that one. Right. But while I'm on series, let's switch over and look at current. Do you guys think that the current has to be the same everywhere in a series circuit?
Yes.
Yes, even if they're different resistances. Even if it's like, let's do a traffic analogy. Okay, suppose I got 1 stoplight here and 10 stoplights here. I got a bunch of cars going around town. Do all the same cars have to go through all the stoplights? Yeah, because there's only one street. That's all that says right there. Okay. How about all right, that's gonna bring us to the junction rule. Let's go to parallel. Guys, suppose let's switch over to amps. Suppose they have 9 amps. I'm just making something up. 9 amps. Okay. And it splits. Now, if these are the same resistance, does it split 4.5 and 4.5?
Yeah.
Yeah. Right. And if they're different resistances, they still have to add up to 9. That's what the junction rule says. So however it splits, it has to add up to the original number of amps. That's all this says here for an amp. Right. Now, the trickiest rule on this whole page is this very bottom line. Right, you guys ready for this one? Now, it makes sense, but you have to think about it a little bit. This says that the current through branch A is proportional to the other resistor, right? Think in terms of traffic lights. Okay, suppose there was 1 traffic light down this street and 10 traffic lights down this street. And there's a stream of traffic. Most of the traffic is going to go which way? Yeah, through the 1 light rather than the 10 lights. But if there's like 100 cars, do you think a few cars are going to say, I'm going to trickle through the bunch of lights because there's too much traffic going that way? Right? And this proportion tells you exactly how the traffic splits. So if I have 9 amps, and let's put 1 ohm here and 2 ohms here. Guys, 1 ohm versus 2 ohms. Do you think that 2/3 of the traffic goes through 1 ohm and 1/3 of the traffic goes through 2 ohms?
Yeah.
Right? Hey guys, what's 1/3 of 9 amps? 3 amps. And what's 2/3 of 9 amps? 6 amps. That's all this says right here. Okay? You guys get that? Okay, is that okay? Alright, there's Kirchhoff rules, there's 2 rules, and all these other ones fall out of this. Okay. Alright, you know what would be really helpful are these waterfall analogies. Okay, so here's 3 resistors in series. You get to one after another in series. Do you guys see that the current, say the flow rate, has to be the same everywhere? If this was a physical waterfall, wouldn't this be the same gallons per minute everywhere? Okay. That's the current. That's this rule right here. Right? Do you guys see that if you add up the voltage drops, that would be the waterfall heights in this case? It adds up to the full height of the cliff. You guys see that? Okay. And that is Kirchhoff's loop rule right here. That's loop rule. You guys see that? Loop rule? Okay. All right, you guys good? Oh yeah. You mean like making this one shorter? Skinnier? Yeah, how skinny or wide it is has to do with the flow rate, which has to be the same for all of them, right? Which is the same as leaving the battery and same going back to the battery, right? And in terms of electricity, it would be amps. So every one of these resistors has the same number of amps going through it. Yeah. So to make one skinnier, they all get skinnier, and you can do that by increasing the overall resistance or decreasing the voltage. Yeah. So that'd be how you could do that, but they would all change the same. Yeah, as long as they're in series, right? We're gonna make some Kirchhoff tables. I made an example. I put in a poster. If you download that book that I put on Google Classroom, it's got all these tables in it. Right? Well, here, let's do this. So I shaded some of these. I have to give these to you. I have to give you the voltage from the battery and the 3 resistors in ohms. Now, once those are locked in place, the battery voltage and 3 resistors, you can figure out what's the voltage drop across each individual one, what's the current through each individual one, what's the power in watts. Now there's a process to get there. Also, what's the equivalent resistance of the entire circuit, right? And these are all interrelated. And there's not necessarily like first step to this, but it's going to be a process. And this is going to be the process that we're going to use to put these together. Right? You guys got that? Okay, got that. For example, suppose I figure out let's do this. Can you guys say 1 + 2 + 3 is 6 as long as they're all in series, right? And if I have 12 volts and 6 ohms is going against in total. Can you guys do Ohm's law? I equals V over R. Guys, what's 12 over 6? 2. That's 2 amps, right? And then let's do Joule's law. P equals IV. What's power is current times voltage. What's 2 times 12? 24. That's probably at 24 watts and leaving the battery. Is that okay? Right? That's at the point of the battery. Okay. Now what about each individual resistor? Is it true that the current's the same everywhere? So 2 amps has to be the same everywhere? This is not the only way to fill out the table. It's just one way to think about it. Okay. Can you guys do Ohm's law? V equals I times R. 2 times 1 is 2. 2 times 2 is 4. 3 times 2 is 6. And look, all the voltages add up to what's 2 + 4 + 6? Adds up to 12, which is the battery. You guys see it works? Right? P equals IV. We'll do those too. I know we're getting real short on time. Here's 3 in parallel and some example numbers in parallel. And then I also have a hybrid and some examples of hybrid. All right. Well, maybe we'll get to this page tomorrow. We're getting there, guys. We're getting there. You guys have a good day. See you guys Friday.